Welcome everybody. As you come in, we'll be underway in a couple of minutes, but thank you so much for joining us for today's webcast, the thermal considerations when designing electrical enclosures. Thanks for joining us. As you come in, if you want to say a quick hi in the chat, if you've been on webcast before, just a quick hello. If you want to say hi where you're logging in from, that would be good. Just name and where you're logging on. Just say hi in the chat. That would be great so people know who's on the call. That'd be awesome. I'll be introducing our presenters shortly as we get into the hour together of deep diving into the thermal considerations when designing electrical enclosures. Also, just remember the Q&A that you'll find as you come into the webcast. You'll find the Q&A button in the kind of center panel down the bottom there of the screen. Please use that at any time. We'll be doing a live Q&A towards the end of our presentations. We want to make this as interactive and as valuable as possible for everybody on the call. So if you have a question, as it pops into your mind, just put it into the Q&A for us to answer as it comes through. So a few folks coming in. Thanks very much for saying hi in the chat. So hi to Vino Rodriguez joining us, Technology FM at Sydney Airport. Brad is coming in as well from Auckland. Good to see our New Zealand friends joining us. Also special hi to Maurice joining us from Brisbane. As you come in, folks, if you want to say a quick hi into the chat, we'll be underway in about a minute when I introduce our presenters today. But as you all come in, thanks for joining us. A great response for our webcast today with Rittal, talking about thermal considerations when designing your electrical enclosures. Hi to Philip joining us again, South Island, New Zealand. Hopefully the weather's great for you guys in New Zealand right now. And also Andrew, hi to you joining us from Foodmark. Nice to see you. Also Perth, WA, a little bit earlier for you guys, but good to see you joining us as well for the webcast today. So we might kick off as folks sort of come in. Please feel free to use the chat at any stage, but obviously use the Q&A mostly for direct questions to our presenters. Anything specifically that you'd like to ask when we get to our Q&A session coming up on our webcast today. So I'd like to kick off by introducing our three panelists today, our three speakers. So firstly, Mark Roberts is a Director of Marketing and IT Sales at Rittal, ANZ. Mark has been with Rittal in the UK and Australia for coming up now to 18 years and has a strong product management background. Since obtaining academic qualifications in systems analysis and design, Mark has increasingly worked on IT and industrial cooling applications during his tenure with Rittal. He is passionate about the reduction of emissions from implementation of efficient cooling solutions. Joining Mark is Peter Kellner. He's the Product Manager for Enclosures and Climate Control at Rittal. Peter is an electrical engineer with over 15 years of experience in product management within the electrical industry, skilled in product development, implementation and market strategies within the electrical market segment. Peter has been with Rittal coming up now for 4 years and has a solid focus on industrial solutions and application-specific results. Also joining us is Tim Anderson, Managing Director of Technology Cooling Proprietary Limited. He carries over 30 years of experience in the field of thermal management and automation and operates a specialist cooling company. Technology Cooling at Rittal serves as partner and supports the customer base in both Australia and New Zealand. He has, and his company has extensive experience in the Rittal cooling equipment product range and provides support, service and maintenance of Rittal's cooling equipment. So a big welcome to Mark, Peter and Tim. Before I kick things off, just a quick poll for you guys, or we're just going to get you just in the chat as you come in. And again, welcome if I haven't officially welcomed you as you've joined the webcast. But in your current role, are you expected to provide climate control as part of your overall solution? Just put a Y for yes or an N for no in the chat for me right now. So everybody on the call, question is, in your current role, are you expected to provide climate control as part of your overall solution? A few yeses coming in there, N if it's a no, but a solid yes and a 10 as well, which is great to see. Just one no, good yeses in there, one or two no's, but mostly yeses. So thanks for contributing to that. We might do a little bit of that interactivity as we go through. But firstly, let me hand over to Mark. Probably to ask Mark first question to you is, I suppose, to set the scene for us, why are we here today talking about climate control?
Yeah, thanks, Tony, for the introductions and the welcome to everyone that's joined us today. Obviously, electrical enclosures are housed in state-of-the-art technology and components and systems, and they're being used in a wide variety of applications, whether that be manufacturing, in transportation, in the resource industry as well. But invariably, they tend to be in harsh environments. And when we're putting these components and these systems in these sealed enclosures, they do become subjected to the high temperatures and also potentially high humidity as well. And that can be generated either by the equipment itself or potentially or the environment. So the result can be an overheating of that. And potentially condensation in the enclosures as well. And that obviously isn't good for the equipment and the asset. So what we're concerned with is making sure that we maximize the lifetime of that piece of equipment, and also ensuring that we don't have a systems failure that is resulting in downtime of a process as well. So we want to make sure that there is a long-term reliability for that equipment by providing an environmentally controlled enclosure that is part of the overall critical nature of the process. Rittal itself has actually been involved in enclosure cooling for more than 30 years, and Peter will take you through some of the product set and applications. But what we really want to do today is share some of those experiences and also help people to understand the tool that we do have available for them that makes the calculation of the actual climate control solution far easier than what it might be for the audience out there. So what I'll do is I'll pass over to Peter, who can take a deep dive into some of the fundamentals and the critical aspects of what we need to consider when specifying a solution.
Thank you, Mark, and good morning, everyone. Thank you for joining today's meeting. My name is Peter Kellner. I have been with Rittal for around 4 years, recently moving into a product management role responsible for enclosures and climate control products. Today's webinar is split into 3 parts. We'll first look at the importance of climate control in an enclosure system, elements required for the thermal management, and then we'll work through an online example of how to apply these elements. And finally, we can have a Q&A or panel discussion session. So today, Rittal, as a system solution supplier, offers much more than just an enclosure system. Rittal is a market and technology leader in climate control systems across many market segments. The products and benefits and features that distinguish us from competitors include not only the range, reliability and safety of our products, but also the energy efficient consumption. These products, along with enclosures and other infrastructure products, are designed to work together in a single system platform. So why is climate control such an important factor in enclosure designs? Research of electrical equipment failures has identified that whilst vibration accounted for 20% of breakdowns, the remaining 80% was caused by temperature, moisture and dust. These 3 factors, adding up to the 80%, can be addressed and minimized by using the appropriate climate control products and or solutions. So whilst climate control is obviously important, how do we begin to tackle the thermal management? First, we need to recognise factors that drive these issues. In doing so, we need to consider the heat load. Generally speaking, there are two sources of heat loads within an enclosure. They are the external heat load, that is driven by the ambient conditions, and it is generally expressed as the maximum air temperature outside the enclosure. Then you will have the internal heat load. This is the heat generated by the electrical equipment within an enclosure. The total of these two will be the total heat load on the system. So a little bit more about internal heat load. Our practical approach in determining the internal heat load value is to examine each and every electrical component. Getting values from manufacturers' data sheets is a straightforward method in finding this. Adding up all the component values will give you your total internal heat load. If exact parts are not known, using data sheets for similar products is also a good start. There are also other methods for determining heat load. One other opportunity is on operational units is to measure temperature. Simultaneously measuring and finding the difference between the internal and external temperatures during load times can also give us the internal heat load value. Okay, moving into the internal ambient temperature that we need to consider. This is often a misunderstood term. However, it simply refers to the desired maximum temperature inside the enclosure. This value is generally defined by manufacturers, and it denotes the optimum temperature that they recommend for the electrical equipment. A practical and internal temperature will minimize failures, downtime, but more importantly, it will extend the product life for equipment. In short, this is the value that the temperature you want to set your limit to within an enclosure. On the opposing end, we want to dissipate or reject heat. Again, there are two methods of doing this. Passive dissipation, this is thermal radial or convection heat dissipation. This occurs naturally through the heat radiated through the enclosure material. Then there is also active cooling, and this is where we introduce some of the Rittal products to aid with pushing out some of the hot air in favour of cooler air. Rittal has a vast selection of products to do this, and as you can see, there are fans, cooling units, liquid cooled packages. Just another note on the thermal radiation and conduction. So the heat transfer is defined by a number of factors. Some of those factors are enclosure size, hence the surface area, the material that is being used. Certain materials will conduct heat better than others. And thirdly, the environment or position of the enclosure. A freestanding enclosure will have more surface area to dissipate heat with. However, this will be a consideration when designing the system. Again, taking a closer look at active heat dissipation. We refer to this as products that actively dissipate heat by using a form of cool air. The graph here gives us a quick visual snapshot of our products on offer. It's a selection graph for cooling power requirements versus environments they are exposed to. Taking a look from the bottom, we have fans and filters, then air conditioners and air to water heat exchangers. With fans and filters, they are capable of working with favourable ambient temperatures, suitable to from clean to moderately dirty environments. On the other end of the scale, you have the air to water heat exchangers that have got a lot more cooling power and are able to cope with harsher environments. So how this transposes into products and expanding on the graph to visualize what products are available. there is a vast selection to choose from. Again, we'll see the fans and filters in the air cooling units. We have AC units or air conditioning systems within the cooling units, and then liquid cooled product. You will notice there are two additions that we have added here. Heaters, in a sense, do not cool, and conversely, they do the opposite, but they are still part of the climate control offer. With fan and filter configurations, they can help counteract issues surrounding condensation and humidity. Essentially, fans on their own are unmanaged devices. They require instructions from other devices, such as thermostats, as to when to turn on and when to turn off. These fall under the accessories area. Another worthwhile mention is the IoT unit, shown on the left near the accessories. Rittal's signature range of cooling products, Blue E and Blue E Plus, have designed an integration into the IoT module to make it truly internet capable. The IoT module provides a real-time bi-directional data where you can get readings of real-life protocols and data. So this brings us to a point where we have compiled all this information ready to be used in a practical solution. So far, we've considered the importance of thermal management, looked at the heat load and what causes them, what drives the temperature up in an enclosure. We have considered our internal temperature. This will be our limit set that we want the temperature to get to within the enclosure. And then we've looked at means of dissipating it. Some of it will occur naturally through the enclosure material, and the balance of it will need to be dealt with an appropriate product that is sized according to the design and environment. So putting this all together is made easy with Rittal's latest tool, Rittal Therm 6.6. And to work through this, I'll hand it over to my colleague, Tim Anderson, who will work through the example. Thank you.
Yeah, hi everyone. Thanks for your time today. As everyone's introduced, my name is Tim. I own a company called Technology Cooling, where we specialise in the thermal management of enclosures. Now, I'm going to provide you with a real user experience. I'm a real customer off the street, and we use this software as a real tool. Now, it's freely available on the internet, and basically you've got options where you can download a full version, you can do a FTP transfer if internet connections are not so great, and most importantly, you can use the smartphone and iPhone apps. However, they don't hold much of a database, and I'll explain that a little bit later as we get through the software. Now, Therm was designed to make calculations easy, but like anything, it's only as good as the information you provide it. Now, I also want to mention that everything we're going to talk about today in this software is expressed in watts, in kilowatts, but they're based on sensible heat factor. We don't discuss or consider latent heat because we're working with enclosed cooling. We don't really regard the impact moisture has on our systems, okay? Of course, we're going to enclose and design systems, you know, to maintain an IP rating. IP rating obviously is to maintain our integrity with dust and whatnot, but it's really important that we get through this software and understand where we can use the correct product with the right tool. So, leading into the software, as I've discussed, the software is just about to start up, so I'll just give it a click. Now, I just get these little warnings up because software is running in the background. Now, when you have downloaded the software and you start her up, this is the first screen that you're going to be introduced with. Now, the first page is pretty straightforward. You input the correct data based on your project. I'm not going to waste time with that. But let me cast your eye to the very bottom here, where you've got the maximum external temperature and the maximum internal temperature. Now, we're going to work on a fan and filter scenario where, by obvious means, the information we put in here, right, will determine, of course, our requirement to using a fan or not, because we're working here on temperature difference. So let me explain. So we've got the maximum external temperature. That's the maximum ambient plus a few degrees, because it might be 45 degrees in Sydney, but in a typical manufacturing environment, they could add 2 or 3 degrees to your maximum external temperature. We're going to use 40 for today. And then we've got the maximum internal temperature of the enclosure, okay? Now these have to be expressed as a difference. If we don't, then we can't use a free cooling method like using fans, okay? It's kind of obvious. Now, also just briefly, the difference in temperature here we express in kelvins as we go further along, okay? So I picked 40 and 45 in there. So I'm going to flick over now to the enclosure selection. So I've inputted these 2 variables, and now we're looking at, okay, what sort of enclosure do we have? Now we're going to pick a real enclosure called the TS, which is standard industrial range, pretty good IP rating. Now, I've picked a standard size here. It's 2 meters high, 800 meters wide, and 600 mil deep. Now, do you see we've got what we call the K factor? Now, the K factor is the ability of a material to absorb and reject heat, okay? So this is a steel walled enclosure, so the K factor is an average of 5.5, okay? And as Peter was saying before, where you put things makes a difference, because it's all good to have a K factor and a surface area, but you might not be able to use all your surface area to reject heat. And of course, the software understands and calculates this accordingly. So we're going to pick this given enclosure. I'm going to save it here. There's a little bit of a time lag between my mouse and the actual screen, so we're just going to wait for that to happen. And it's coming. Okay, this is one of those times when you're on air and everything's going to plan, and it's not, because the little screen is saying, yeah, all good. So I'm just going to bring us back to where we were, and hopefully, yes. So we've saved our enclosure, running backwards. And once we've saved our enclosure, the software prompts us to input how much heat, load, or loss. Now, the German translation of loss is the fact that they understand that all technical equipment, when it's used, rejects heat. And that is a loss of heat from the equipment. In English, we kind of use the word heat load, right? It's the same thing, it's just a bit of a German English translation. Now, if you know what the value is, you can put it straight in here. Or we can look at this. We can look at the measured temperature. So if you had a thermal imaging camera or even some basic sensor probes, you'd be able to firstly measure the internal temperature. It might come back as 50 degrees in this example, and your external temperature is 20 degrees. So do you see that we'll have a 30 Kelvin or 30 K difference, yeah? Now, that would pretty much signify quite a heat load, and understanding that size of enclosure, I'm guessing that heat load could be around 1 kilowatt, but we'll see what the actual software says, yeah? So then going a little bit further along, we can also, rather than measuring the temperature to determine our heat load inside there, we can actually go through Rittal's database. And this is where the phone app doesn't have access to this. You can only do it through direct input. But if you download the full version, it runs straight off, and you can actually pretty much go in and pick certain devices. Now, because we're talking about, technical products, I'm going to start with basic electrical. So I can actually pick for example, a circuit breaker, and then determine, based on the size, yep, which is 80 amp circuit breaker, and that would correspond over here. It says 14 watts of heat, which is very almost insignificant, but one enclosure wouldn't have one circuit breaker. So when you start adding things up, you'll be surprised. Now, most of the heat loads I come across in the field are more generated by inverters, frequency inverters, anything from robots. You know, once you start mixing around and changing frequencies, or breaking loads, you end up with a lot of heat. Now, I just want to explain that a little bit again on the German English translation. Inverters are regarded by Germans as converters, okay? So I picked in the general group converters, and then I'm going to pick a drive size, because drives are pretty much going to be our biggest heat load for the day. Because I'm using a fan and filter setup, I'm going to pick something around 22 kilowatts, 22 kVA. Now, if you throw power factor at that, of course, you'll get your kilowatts, and you'll see a capacity load of 100%. Most drives don't work all the time at 100%. So we would change that figure to 80% as an example. We'll just do that once, and then we're going to add this device, okay? So this device here has become our most significant heat load, right? Now we're going to accept all this, and we're going to provide a calculation. Now, going back to this, I said the maximum external temperature could only be 40 degrees, so it might be somewhere in Tasmania or Victoria, even though they do get odd hot days. And then you've got the maximum internal temperature of 45. I'm bringing you back to that because it's going to affect our calculation. Now, we're going to hit the calculation button, and once this screen's presented, you've got all this wonderful, exciting information. Now, you'll see that starting to the top, the software's calculated the surface area. Based on its K factor, it's also determined, if you don't put any cooling on this, it can dissipate about 140 watts of heat through its surface area. But if you also look, it's also giving you a nice heat load figure of 474 watts, okay? Now, you'll notice here, you've got these little green, well, not red crosses, but green crosses. So let's pick a fan, okay? Because that's an example. Now, you'll notice here, it's provided us with a list of fans, and you'll notice that we've got the word power here. Because I'm talking to a lot of design engineers, that power is really what they're talking about is cooling power. But in our world, we're talking about flow because, we look at meters cubed per hour. So I just want to clarify that. So that's got nothing to do with power. This is a flow rate. Now, you'll also see above here, we've got the sea level. So very quickly, if we actually change this to 1,000 meters, you'll notice that our figure is 348. And then if I go higher in elevation, because we can't always assume they're at sea level, right? So you'll notice that these figures change. Now, it's 406 meters cubed per hour. And if I go to sea level, it drops to 330 because obviously as you go higher, the air gets less dense and you need more of it, right, to do the same amount of things. So this is actually a new feature of Therm that they've added in. Now, our little project, we're going to pick the actual, based on a normal sea level of say 100 meters, and we're going to pick the first option, and we can accept that. Now, you will see that it's actually picked the products that it wants you to use. Now, when we talk about using fans, we also, on the design table, we've got to look at IP ratings, okay? Now, Rittal's fans are designed to draw over face, and you might be doing the engineering of a box that holds $1 million worth of equipment in it, right? And the concept is fans draw over face because we want to pressurize the cabinet to a degree and then use natural convection heat for the heat to dissipate out the top of the enclosure. And that way you're not relying on all the door seals. So these are like little engineering tips I'm sort of throwing you at the, on the way, but it's a common question because most people think to get, heat out of an enclosed space, you need to extract it. But we work on the principle we'd rather like pressurize it and let it push out, yeah? So without going on about that too much, let's get back to these fans. So I was able to pick these two fans based on a heat load of 474 watts, okay? Now, I've got other options here. I could actually use a cooling unit, but in this case, I wouldn't because dust really isn't a problem. I don't have a high IP rating to worry about, and my equipment can sit up to 45 degrees without hurting itself. Now, let's change this somewhat. So let's just say, to be realistic in Australia, we'd be looking at around a 50-degree maximum ambient, right, on the day, and we'd be looking at more likely to have a maximum internal temperature of 45. Now, do you see what's happened with the software? We've lost our fan options. We've lost an air-to-air heat exchanger, and now we're in a cooling unit world, or, sorry, that's a bit of a misclick there. Now we're in a cooling unit world down at, air-water heat exchanging, and yes, heating is still an option, right? And I'll come to that in a minute. Now, let's pick cooling. So I click on a cooling unit, and we've got a whole range of options here. So Rittal has got 2 cooling unit products in this series, and you'll notice once again it's picked the Blue E Plus, right? And it's saying that you need around 860 watts of cooling out of this unit, okay? Now, if we look at the technical information of the unit, it'll give us a brief summary about its cooling capacity. So, yep, the software has calculated the required cooling capacity, but can your machine give it to you? So I'll explain this quickly. Do you see that you've got L35 and L50 on the screen here at the top? Do you see how the equipment derates itself? Look, Rittal's really honest about the fact that when you cool at 35 degrees, you can provide a kilowatt of cooling very easily. But that's not really the case. Like most of the equipment we work on or to have to design for are looking more at 50-degree ambience. And that's what the L50 there is for. So do you see that even though this unit can produce at 0.085 kilowatts on 35-degree day, at 50 degrees, it can't get near there. It's more likely to be 0.67. So that's why it's so important that you put the right variables in that beginning screen, even though you can change it later. Now, the units that it's picked at the bottom are, let's just, won't say the low end, but the industrial range of Rittal's basic range, which you call the Blue E or top therm. And then you've got the Blue E Plus. Now, this guy is actually, from this series up, they've got variable speed compressors, so they can actually follow the heat load a lot more accurately. Now, because you don't want to put too big a cooling capacity over a unit requirement of half its value, for example, because you'll promote short cycling and all sorts of horrible things. Now, the other thing this software now has a benefit is the NEMA 4X. Now, it's not a standard that we know too much about in Australia, but it's coming into our world. In Australia, if you look out to the right, we talk in IP ratings, but in America, they talk in NEMA 4X, yeah, or NEMA ratings. And NEMA 4X is the highest rating because it covers an extreme temperature range, and it also covers ice and snow and whatnot. So I'll just flip that on and off. So you've actually got choices, not just in your capacity, but you've also got choices in your IP ratings. Excuse me, I'll continue. So I'm going to pick the Blue E Plus here and accept that, okay? Now, it's just told me that, you've changed your parameters from the original. Yep, that's correct, because we moved the ambience. Now, it's actually picked a cooling unit for you. Well, sorry, I picked this one, the 3361 earlier, And now we can go a little bit further with the calculation. Now, Rittal, of course, being a sales organization, promptly bring you up with a whole range of different, features that you can add to the software. And onto shopping list, of course. But I'm going to go a little bit further in here, and you'll come to the summary when I go and click this guy. And you'll see in the summary, it's pretty much giving you the information that we've input, right? It's given us voltage, I left at 400 volts or 415. We can go back and pick a 240 if we like. And it just gives you a little bit of summary of what we actually did. And most importantly, it gives you an idea of what size cooling unit you need in this example, okay? So basically, that's like a completed quick rundown on therm. Now, I just want to come back to the calculation and cover the heating, okay? Because you'd wonder why on earth would we care about heating. Now, I mentioned early on, we don't worry about latent heat because we regard this system to be a sealed enclosure. Moisture doesn't incorporate itself into our calculations, but we still got to worry about condensation in cold mornings. And I know of an example with speed cameras where, they produce a lot of heat when they're chopping away at us, but on a cold morning, the inside of the actual camera enclosure will condensate and could cause all sorts of damage, nicely. Anyway, carrying on, we've got a minimum external temperature represented here as 5, and we don't really want to go plus 10 degrees in the morning to, kind of avoid condensation and whatnot. So it can even select a heater for you, and you can add that to your report as well. So, yep, it's picked a nice little heater for us. We have the cooling unit option because I changed the fact that, realistically, we're going to have very high temperatures and we can't use fan and filters. Now, as we get to the actual end, then basically I can produce in the summary, okay, I'm just getting over towards the summary. You'll notice down the bottom here, we've got all these export formats. Now, one thing I didn't touch on is this software is a very powerful tool in the fact that Rittal Germany have followed all the IEC standards. Rittal is a very proud company in the fact that standards are everything. They cover all the IEC standards, and they quite proud in the fact that pretty much any equipment you buy from Rittal in the cooling world will have all the standards appropriate to Australian standards. So now that I've looked at this, it'd be kind of nice to put this in a nice report, and you ring up Rittal, get a price on this product, whatnot, and you can prepare a quote. And then I'm just waiting for this to open. And here we are. The software has nicely produced a report in a PDF version. It's just a summary of the information I've shown you before. Again, it's picked the enclosure, it's picked the height, whatnot. It's told your client, like, this is how nasty things will get if you don't do anything about cooling. And to be honest, if you put 1,000 watts of heat into a cubic meter and leave it, you can get temperatures up to around 200 degrees if you leave it there for long enough. So, of course, going through this report, you pretty much can see that all the information's been captured. Now, I've pretty much given you a very basic view of therm. And again, this is my first webinar, so I was kind of excited about doing this. I think we've gone a little bit quick, but that might be a good time to actually get onto some Q&A. So I'm going to hand you back to Tony.
Awesome, fantastic. Thank you very much, Tim. You sound like this is not your first webinar because you did very, very well. Fantastic. Live demonstrations are always the hardest thing for anybody to do on live television or a webcast, but you did very, very well. Thank you. And also thanks to Peter for your presentation. We are going to jump into Q&A, and we've got a good solid 20 minutes. There's already a few questions coming into the Q&A panel, but I've got a question for the attendees first, everybody on there. If you can just have a look in chat, the question for you very, very simply is, what is the biggest challenge you have carrying out climate control calculations? What is the biggest challenge? And I'm just going to get you to answer 1, 2, or 3. Number 1 is not having sufficient data, put a 1. 2, not being fully conversant in mechanical engineering. And 3 is nothing, you're in total control. Climate control calculations are where you want to be. So just in the chat for me, number 1, 2, or 3, answering that question. 1, you don't have sufficient data is your biggest challenge to give a base calculation. 2, not being fully conversant in mechanical engineering. Or 3, you're fully confident and you know what you're doing with climate control calculations. All right, so a few coming in there, which is great. Just for our panelists as well, it's going to be good for a conversation. So number 1, it seems quite a few of attendees not having sufficient data upon which to base the calculation, and some are also not fully conversant in mechanical engineering. So that's great. So we're going to open up to a panel discussion. We actually do have a few questions in there, but I've got a first question to kick off with Tim. If I can sort of start with you, can therm be used when designing outdoor enclosures?
Okay, Tony, it's a great question. The answer is absolutely no, because you may not have noticed, or you may have noticed, that all the talk I did was based on an ambient condition, okay? Now, if we start putting enclosed heat loads outside, then we get a lot of solar influence, and that could be 2 or 3 times whatever therm calculates, because therm is not designed for solar. Now, if you do have solar requirements or outdoor heat load calculation requirements, then Rittal do offer this service, and you would actually send us an email with your variables, and we'd make contact with you. And sometimes I help Rittal with these types of things.
Awesome. I will start with a question. I'm not sure who's going to be best to answer this, but I'm going to go from the top with some of the questions from our attendees. From Harold, the question is, what is the K value for 1.5 millimeter 316 stainless? Very specific question. Is that too specific?
Who's answering that one? I'll answer that one. It's a really specific question because technically the K factor was expressed at 5.5. That was for just under a mil mild steel. And when you get into stainless, I could ask you 3 other questions. Is it mirrored? Is it brushed? Because they all have different K factors. But if you're talking stainless, K factor you could use, unless it's not mirrored, is around 6, not 1. Yeah.
Awesome, thank you.
If you also pick a stainless product out of the Therm Rittal enclosure database, it will automatically tell you as well what the actual Rittal K factor is for our stainless. So again, it's designed to try and support you in choosing and not having to worry about some of those specifics.
Awesome, thank you. Mark, actually a question for you. Is the software suitable for Rittal IT products?
I don't like these answers because it's a yes and no. When we're talking, Tim highlighted some Bluey Plus product, and for those type of environments, absolutely, our Bluey Plus is used in our micro edge type of applications. So it might be in a warehouse, it might be in a factory floor where we're seeing more and more IT being deployed. For those kind of applications, absolutely yes. But the software, again, as touched on by the guys, is really designed for sealed environments. Most IT environments being open or utilizing in-row cooling or crack units. Then we have some other software on the website again that helps us when we're specifying chilled water product. But again, we tend to work with clients who have those specific applications. So yeah, it's a bit of a yes and no on that one.
Sitting on the fence with that one.
Yeah.
Okay. Open question to any of the panelists. Want to jump on this one from Alan Morton earlier on in chat. How do you account for sun shields on outdoor enclosures? Who wants to take that one?
I'm happy to.
Okay, Tim, you answer first.
Okay, I can even give you a sales ball there, Mark. So to answer the question, we normally use aluminium as a material, and Rittal have actually got a product range called the CS range, and that's what they class as a double-skinned enclosure. So the outer enclosure wall is actually made of alloy to absorb reject heat, and the inner will work in the opposite direction. So yeah, to answer the question, Rittal do a product range, it's called CS, and that does what we call heat or solar shields.
Just to add on to that, and also on to the earlier question regarding outdoor. So when the calculations or requests for outdoor enclosures come in, as Tim mentioned, it's really important for us to understand the radiant heat and the solar impact. So we've actually got some software that the guys in headquarter run, and we're able to give you accurate information, again, to the same level that Therm does and a little bit more. But unfortunately, the software is very specific and can only be run by our engineers over in Germany. It normally takes about a 24, 48 hour turnaround. So normally quite a quick response for any of those applications.
Awesome, thank you. A question again from the attendees. It is a bit of a detailed question, probably relating back to the demo. So maybe Tim, one for you. The question relates to K factor in the calculator. What is Rittal's view on enclosure installation and vapor sealing construction for applications where we expect the internal temperature to be higher than external temperature for large proportion of the year?
Okay, it's an odd question. The software calculates pretty much everything that's been asked in that question, okay? But the K factor is just a factor, you know, to express the material's abilities or properties to reject or absorb heat. So it's as simple as the hotter the ambient, the more heat that you can, you know, absorb, right? But on the other note is, if you want to run at a higher temperature internally and your ambient's not that high, then you can use your walls to reject heat. And that's why the K factor works both ways. So the software will answer all those questions if you give it those different variables.
If I could, sorry, to just add on to that as well. We did have a recent instance where that was a requirement for an outdoor battery application, where they wanted to add or utilize only a single skin enclosure, but utilize some insulation. We can provide a calculation on that. But again, it needs to be done by our colleagues at the headquarter. And whereas the software that you see in the program that you see working here is all based on the IEC standards, the method of calculation that is more theoretical, but it can be done to that kind of level.
Awesome. Thank you. Quick question, talking about the software there for a second. Peter, quick question for you. Does Therm work on a Mac?
Thank you, Tony. And no, it does not. The software is available to be downloaded for free. It can be used as a standalone package, or it can be used online. Now, the package can be downloaded onto a number of devices, that being tablets or phones, but there is no Mac version that can be utilized in that sense. So Mac users can utilize their iPads or iPhones, whereas with PCs, you can either run it online or as a standalone software. The obvious advantage with using it online is that updates are live, and any changes, any updates to the software can be as up to date as possible.
Awesome, thank you for that. So yeah, obviously a way for Apple users as well. A question from Andrew Nichols: what are the main considerations when determining heating applications to stop condensation?
Oh, I can answer that. Of course, the moisture content of the air. Okay, so humidity is your first factor, and then your second is based on your ambient temperature and your humidity, you can work out what the dew point is. And the dew point is the temperature at which the vapor in the air turns to a liquid. So we do that calculation, and Therm can do that. If you look at the very first, there was something on humidity. So you work out what the dew point is, and if you keep your temperatures above your dew point, then you don't risk any condensation.
To add to that, Tony, we also showed a thermostat accessory that measures temperature. Within the accessory range, we also have the hygrostat, which will measure humidity. So that can work hand in hand in managing not only temperature, but humidity within an enclosure.
Awesome, thank you for that. 9 minutes left, guys, towards the end of our webcast today. So if you do any burning questions, please put them in the Q&A. It makes it a little bit easier for me jumping from chat to Q&A if they're all in one place. But question from Craig: please explain the advantages for fan and filter pressurization and over extraction. Which is more efficient?
Okay, I'll answer that one. By drawing air in and pressurizing the cabinet, you take away all your concerns about your door seals or any openings in the actual cabinet. Now, most importantly, the air that you're drawing in, you're controlling that air quality because you're filtering it, okay? So you're using a nice filtered air to pressurize the cabinet, right, to stop any infiltration coming from anywhere else. And then that way, by over-pressurizing the cabinet, then the natural convection, methods of putting the outlets at the top of the enclosure and promoting that heat transfer. And that's, as I said in my talk, that's why Rittal's fans are quite misunderstood, because they'll come straight out of the box, designed for drawing air over face, okay? So hopefully that answers the question. You control the air that you bring in this way, and you're able to filter it.
There were a couple of questions actually around, I might try and combine these together around fans and filters actually. One was around the ideal installation of fans and filters, fans on top or bottom or side of the panel. And is there a type tested documentation that indicates thermal UV performance of CS outdoor enclosures?
Okay, I'll just answer the UV, all that information. Again, you just contact Rittal, because the CS range does meet a lot of the standards. I can't say exactly which ones. A lot of that information is also available on the actual Rittal website, without saying that. Now, sorry, can you just repeat the other question again, Tony?
Yeah, so it was around what's the ideal installation for fans and filters?
Okay, that's an easy one to answer.
Yep.
So basically, you would install the fan straight out of the box at the lower point of your enclosure, and that's where you're drawing air in. And then the relief, or what we call the filter side, because it's two parts, two components. The filter side is mounted at the top of the enclosure. But I want to explain that the reason why there's a filter in the relief, it's to provide the product with an IP rating. Because you imagine if it was a Luvid, just, without any media in it, dust and water could actually make its way into the enclosure when the fans aren't running. Now, just on saying that, one of the most basic ways for saving money in energy is most switchboard designers design their fans to run all the time, and understand when they're running, they're actually drawing dust and they're actually using power when their process is not running. So it sounds odd, but it's not unusual to see $1 million system with, you know, a beautiful new fan and filter system that just runs day and night because it is fed directly off the power and not off the process. So again, Rittal's got a product, as Peter mentioned. It's got a basic thermostat. Fan can be turned on and off with temperature. So I'm just adding that to answer the question basically, but there's a little bit of an engineering, you know, energy saving tip there.
Awesome. Thank you, Tim. A question from Morris. When you select the rating of the respective equipment, for example, 80 AMP, MCCB, does it assume this is running at full load? And I don't forget this bit right. You derated or derated the converter, but not the other equipment.
Yes, I was only doing that by example, but you are quite right. That factor that I showed you that was, it had 100% on it. I was able to, you know, you can lower that rating on everything. So that rating is almost like if you're using kVA, you set it to your power factor, it gives you kilowatts. If you use that in just a straight electrical component, it's based on the usage of the component. So, you know, 53 amp, a 60 amp circuit breaker as an example, doesn't have 60 amps of current draws through it all the time. So you would, you know, pick that device and then probably set it to 50% because things are always generally overrated that much. So that answers the question.
Awesome. Peter, I don't know if this is one for you. What is the correct method to pick the right filter for fans?
The software will also aid in doing this. So basically, the calculation will give you an airflow that is required to handle the system, as well as the dust and environment. So in picking the appropriate filters that go with the fan units, we'll need to match the size in terms of volumetric airflow and dust and oily environments.
Awesome, thank you. Last couple of quick questions in the closing minutes we have, and again, thanks for everybody for being super active on the Q&A, and they're still going. So we might, if we don't get to your question, we will share these with the panelists, and we can reply to you guys directly. Just one from Peter, I think it is. Is there merit in using variable fan speed for cabinet cooling against the cabinet internal temperature, and do Rittal offer a product for this?
You want to answer that?
Yes, within the fan range, we have two selections. We have the standard fan range and the electrically commutated fans, which can be, where the speed can be controlled by a device. And so that means they don't run at 100% capacity at all times. They can ramp up, ramp down. They have a soft start function, and hence enabling their lifespan. So there are fans available for that application.
Awesome, thank you. Now, what have I got here? Finally, what can I do? What's the IP rating of air vents without filters?
It's your product, you go for it.
No one wants to answer that one.
It's a really loaded question.
It is.
Do you want to pass on that?
Well, there's 3 different IP ratings depending on what accessories. So if you get it out of the box, depending on the product, you can start with an IP rating as low as 35 and up, right? And you can get, with the Rittal product range, you can get up to IP ratings over 55, 56, depending on this. For example, you use a fan and filter, you use a high-grade media, right, under 10 microns, then you add to it a weatherproof hood, and then all of a sudden you got an IP rating over 56. So it's a loaded question because it depends on what, you know, products you use together with Rittal to get that IP rating.
Good to end with a loaded question. There we go. But there's a bunch of questions still in there. And as I said, we will share these with the panelists and come back to everybody. But just wanted to close off on time and thanks everybody for joining us. A big thank you to Mark Roberts and Peter Kellner from Rittal, and also Tim Anderson from Technology Calling for doing a fantastic first webcast demo live. And also thanks to everybody for joining us. In your inbox, you will see a survey following this. Please just take a few minutes to give us your feedback on today's presentation. Just 4 or 5 questions in your inbox, so we know what to do more of and how to make this more useful for you in the future. But from today's webcast, have a fantastic day. Thanks for joining us and being part of this webcast.
Thank you.
Thank you. Thank you. Thank you.